All right, last class period, I started talking about magnets and how cool they are. Today we're going to start doing the stuff that's fun but not easy, right? Yesterday, was there any equations we used? No, there wasn't. But we did have things about understanding what a magnetic field is, what direction it goes, and things like that. So today we're going to start talking about magnetic force. And you might remember from yesterday, I said we are not going to have situations where we calculate the force between two magnets. We're going to calculate the force on moving charges. So that's the title today, magnetic force on a moving charge. So first, with the electric force, we defined an electric field. With the gravitational force, we defined a gravitational field. And those two had the relationship that the gravitational field was equal to the gravitational force divided by the gravitational charge, which was mass. The electric field was equal to the electric force divided by the electric charge, which we call charge. Magnetic field and magnetic force do not have the same relationship. The reason is magnetic force is a weird one. Magnetic force depends on speed. If the speed is 0, there's no magnetic force on a charged particle. It has to be moving, or the magnetic field has to be changing, for there to be a force on the charged particle. Second is the direction of the force. The direction of the force is not the same direction as the magnetic field. Remember, with the electric field and the gravitational field, the force was the same direction as the field. With the magnetic force is perpendicular to the magnetic field, and at the same time perpendicular to the velocity of the particle. So this is a whole different ball of wax. It's more complicated than the electric force. So, yes, this says just the rest of the things I just said out loud. Here's the equation for the magnetic force. The magnetic force is equal to QV cross B. If you don't have a vector sign, that would just be Q times B times B. That cross would be multiplied if there's no vector sign. But with a vector sign, that means something completely different. So it's important to know to put vector signs on your vectors, and to know that if you have two vectors, you can't just multiply two vectors. That's not an option. You can't multiply a direction by a direction. But you can take a vector product, which would be either a dot product or a cross product. A dot product was multiplying the parts that are in the same direction. The cross product was multiplying the parts that are perpendicular to each other. Where have we already seen dot products? Work was force dot distance. It was the force times the distance parallel to the motion. Where did we see cross products? Torque. Because torque was the perpendicular lever arm crossed with the force, multiplied by the perpendicular component. So we're going to have to use the same things we learned for torque, to bring them back. So the force is QV cross B. The magnitude of the force is QVB, sine of the angle between the velocity and the magnetic field. So it's easy to calculate how strong the force is. But you also have to determine the direction. And so my next couple slides are going to go through how we determine the magnitude and direction more carefully. As a general rule, the force is perpendicular to both V and B. Use the right-hand rule to find which of the two directions perpendicular to V and B it'll be. And then you have to reverse the direction if Q is negative. Why reverse the direction if Q is negative? It's actually really obvious if you look at the equation in the box. The right-hand rule will tell you the direction of what? V cross B. But then it's multiplied by Q. And if Q is negative, that means you're in the negative V cross B direction. Negative direction means reversing the direction. So, first, things about the cross product. We've already seen them, but just a reminder, the magnitude of the cross product is, and I rearranged the slides and I just realized I shouldn't have put it where I did. I'll have a figure that shows the derivation of this coming up in just a moment. Remember these signs that when we were in high school we learned were absolute value signs? Now that we're a little more advanced in high school, they mean magnitude. Magnitude means it doesn't have the direction, it's just how big the number is with its units. One of the things that's important to note is the order matters. If you change the order of the items in the cross product, you reverse the direction. So A cross B is in the opposite direction from B cross A. So when you're doing this equation, it's important to always do V cross B, not B cross V. I know those two sound so similar. If I was speaking in Spanish, they'd be the same thing, in fact, wouldn't they? V and B, aren't they the same in Spanish? Japanese, they just only have one of those sounds to begin with. Yeah, for the most part. So how do we get the direction? We've already done a lot of work with the right-hand rule before, but as a reminder, you take your hand, make your fingers point straight out, and orient your hand so your fingers or your index finger is pointing the direction of the first item in the cross product. So since we have the equation force vector is equal to Q V vector cross B vector, then my index finger is going in the direction of the velocity of my particle. And then keeping my index finger in that direction, I rotate my hand so I can point my middle fingers in the direction of the second item, which is the magnetic field. And then keeping my index finger and my thumb perpendicular to each other and perpendicular to the plane of this as well. My thumb points the direction of the answer. Now, things that are important, the velocity is not always perpendicular to the magnetic field. So you're not always going to be having a right angle between these two. But you can move your B anywhere from right next to your index finger to pointing back opposite your index finger. If it's not in that range, you have to rotate your hand around so it's in that range. So that's that right-hand rule, and we will practice it here coming up. For the magnitude, right, I should have put this one first. The magnitude, we have two vectors, V and B. Notice the angle between these two is not 90 degrees. And so we need to find how much is perpendicular. So there are two different pictures here. This picture here is the component of V that is perpendicular to B. That's what the first one is. So V sine theta is the perpendicular component. The second picture is the component of B that is perpendicular to V. But in both cases, it was sine of the angle I used to find the opposite side of my triangle. And so no matter which one you do, you're going to have Q times V times B times sine of the angle between the two. So the magnitude, notice they put absolute value on the Q because we don't want to put a negative magnitude. QVB. Just like with the electric force, I told you, just calculate the magnitude and calculate the direction separately. Do the same thing with magnetic field. So you just get the magnitude, no minus signs involved. So the magnitude is QV, B, sine of the angle between them. I guess I should circle that one too, because that has B perpendicular, which means B sine theta. Now let's look at this picture and determine what direction the magnetic field, or excuse me, the force is going to be. So our equation is force equals Q V cross B. And let us presume Q is positive. So I use the right-hand rule. And let's go to Hannah. I'm not sure how much of the row behind I used when we were doing circuits, but We've got at least a Megan, I think. So Hannah, just looking at this picture because it doesn't have any extra and all of them are the same. If I'm going to use my right hand rule, I take my right hand, first thing because people can make mistakes and use their left hand. And how do I orient my hand to start?
Your thumb is in the direction of velocity.
Not your thumb. Your Katie that's sitting next to Hannah. Which finger goes the same direction as velocity? Index. You orient your hand so your index finger is parallel to velocity. So I got my hand like this. Okay? Isaac, what do I do next?
Make sure your thumb is perpendicular to your velocity.
Which throughout we need to do that.
Mm-hmm. And then where your thumb is pointing, forget where your thumb points to.
Let's not worry about the thumb right now because that's not the one you need to worry about. The next step, we have our index finger is parallel to the first item in the cross product, which was V. So then what finger do I go to? If not the thumb, it must be middle finger. And what direction should the middle finger point? Direction of the second one, which is B. So I have my index finger pointing parallel to B, and then I need to orient my hand so I can bend my middle finger to point that direction. Obviously, if I go like this, I can't bend my finger to point in the direction of B. I have to bend it like this, then I can bend my fingers, and I have those two. And now comes the part Isaac was talking about. I got to make sure my thumb is perpendicular to those two. I bring my hand back because now it's not stretched out, and I can put my thumb there. The thumb points the direction of the force. Well, technically it points the direction of V cross B. If Q is positive, it's pointing the direction of the force. What if Q is negative? It would reverse it. So my thumb was pointing out of the screen. So the force of a positive charge moving in this direction in a magnetic field pointing that direction would be out of the screen. So that's how we get the directions. And it's important. We're going to have at least, well, one question will be explicit on this. You'll have to, what direction is, the force if you have this charge with this velocity and this magnetic field. So you'll have to be able to do this on the test. Not the test next week, but the one after that. I did put up a review questions, one question from each section that was available for you to review on homework, as Jordan requested. Amala?
Is it for extra credit?
Yeah, it'll be small extra credit again. Okay, so you need to be able to use that right hand rule. So make sure you memorize the steps. Index finger, the direction of the first item in the cross product. Middle finger, direction of the second item in the cross product. Thumb in the direction of the result of the cross product. Now, when you're doing a test, remember that you can rotate your paper. So you don't have to sit here with your hand like this. You can rotate the paper around and make it easier, okay? Because, problems will have random directions, and sometimes those directions are things that are really uncomfortable if you just look at the paper from one orientation. So remember that when you're working problems so you don't end up trying to contort yourself. Now the units. I told you that the standard unit is the Tesla, named after Nikola Tesla. Well, now, with our equation, since force is equal to QV cross B, then the force magnitude is equal to QVB. So that means I should be able to calculate the units of B just by rearranging. So the units of B have to be units of force over QV. That would give me newtons over coulombs times meters per second, which you see written right there. And a coulomb per second is an ampere. And so we rearrange the seconds, bring them over to under the coulombs, and say, that's an amp. So 1 Tesla is a Newton per amp meter. Now, as a point of obscure fact, the amp is the SI base unit. The coulomb is considered a derived unit based on the ampere. So this is the base unit, The Newton is not a base unit, right? Newton is kilogram meters per second squared. So I can extend this to get in base units. 1 kilogram meter per second squared over amp times meter equals 1 kilogram over amp times second squared. That is the Tesla in base units. Understand? All right. Direction symbols. We've moved into an area where we're going to be doing a lot of stuff in all three dimensions now. Because the velocity, the magnetic field, and the force are perpendicular, that's going to require 3 dimensions. And so for symbols, when we're indicating into or out of the page, into the page is a circle with an X in it. Or this shows an X by itself, but almost always it's going to be a circle with an X in it. What you're supposed to think of is of an arrow. So we use arrows for left and right, up and down. Up and down now is up on the page and down on the page, not vertical. And then if there was an arrow coming toward me, what would I see? I'd see the point of the arrow. So this here is supposed to be the point of an arrow coming toward me. This here is supposed to be the tail of an arrow moving away from me. So, going off of Gabriel's last name, that's supposed to be the fletchings of the arrow that we see. So when you see those, it's important that you know what they mean, that you're not like, I don't know what direction that means. So it's just a nomenclature point. Some rules for how to solve problems with magnetic force. First, if the magnetic force is 0, if the velocity is 0. Doesn't matter what your charge is, what your magnetic field is. If the velocity is 0, your force is 0. If the velocity has no component perpendicular to the magnetic field, the force will also be 0. And of course, if the magnetic field is 0, it'll be 0. So what that's taking is the magnitude is QVB, sine of the angle in between. So if V is 0, if B is 0, or if sine theta is 0, are the 3 situations that allow you to answer instantly. I've got this situation, it's going to have 0 magnetic force. Most of your problems won't have that, right? You may have one just to check, but mostly they're going to be ones that otherwise have a force. So then you need to determine the angle between the velocity and the magnetic field. And it does not matter if you measure the angle this way or this way. It doesn't matter if it's positive or negative. You're just finding the angle between them. So I always use a positive angle there. So you find that angle and then calculate the magnitude of the force. Then use the right-hand rule to determine the direction of V cross B. And finally, remember that if you have a negative charge, the force is the opposite direction of V cross B. So those are steps for how to solve a problem with magnetic force. Once you've gone through that, then you're going to rely on other things you've learned about forces, like Newton's second law, the force of gravity, to do other things with the problem. But you have to be able to calculate the magnetic force. That's our goal for this section. Then everything else just building on previous material. So I have 3 clicker questions, one right after the other. So the first one, a positive, I should have put this in red. A positive charge travels east. And just in case people get confused, there's our directions. Up is coming out of the screen, down is going into the screen. So it's traveling east in a region where the magnetic field points down. I'm actually going to draw these. So my velocity is like this, and the magnetic field points down. Yes. Because some people put it in the south direction and then you get the wrong answer because you have magnetic field in the wrong direction. So with those, what direction is the force and the charge? 3 people, 2 people, 1 person. And I don't want people to feel bad when I'm waiting for you. You know, you are thinking, and that's what you're supposed to be doing. Whoops. Everything's shifted by 1. Okay, because we had a large group that all said the same thing, I'm just going to go to Sandy. Okay, Sandy put north and why? Okay, now lead us through it. I haven't done it yet myself. lead us through it. So, our right hand, what direction should I start with what finger? Points? Her finger's pointing this way, let the record show. So my index finger is pointing east.
And then you put your middle finger towards the
Oh, you said B. I said D, and I was waiting for the next word. B. Excellent. Your thumb points the direction of V cross B, and because it's a positive charge, it's the same direction. So that was perfect. Now the next question. It's all the same except for we change it to a negative charge. Okay, somebody changed at the last second. Even though it was close to unanimous, I'm going to call on somebody. That somebody's going to be Carrie. Carrie, what was your answer and why?
It's south because your next finger is still east, and the rest of your fingers going into the face, which leaves your thumb pointing north, but it's negative charge, so opposite.
Okay, same rules, but we had to remember because of the negative charge, it's the opposite direction. Perfect. Last of our clicker questions for today. A positive charge travels east in a region where the magnetic field points east. So now we have that. Your answer's in there, Paris. You don't have to worry. Okay, everybody's answered. We have not as much agreement this time. So discuss with your friends. Let them convince you or you convince them. Okay, let's go ahead and answer this again. See if answers move toward right or wrong. Okay, all but one person the second time around said that. One person said north. So, Caitlin, Toy, I have to be clear on which Caitlin. What'd you answer?
I answered A.
And why? Because what?
There's no force, right?
But that's correct. There is no force, but what's the reason? Okay, somebody want to help her out? There's no parallel or perpendicular components, and the cross product is only multiplying the perpendicular parts. So if there's no perpendicular part, then you have no force. All right, enough clicker questions for today. How do you like my spelling of example? I'm pretty proud. Yeah, E's an overrated letter. It's everywhere anyway. Okay, suppose that a proton is moving straight down directly toward the equator. I mentioned this in last class period, right? This is a real problem. So we have a particle that's coming toward us. Note the picture out here is showing north, south, down, and up. So that means we're going to have east is coming, west is coming out towards us, and east is going in. And it asks, what is the direction of the magnetic force in the proton due to the Earth's magnetic field? So let's see. I think it will. Did you answer last time, Aaron? Okay, so Aaron, how do we determine the direction of the force on the proton? Okay, so using your right hand, let's do the whole thing. Index finger points what way?
To the down direction.
To the down direction. And then your middle finger points? Your thumb points?
Perpendicular to both, so south.
No, it's in. You've got to keep your thumb pointing out this way. Not you're bending it like this. You got to keep it out there. Don't go. Bring it around so you can read. Yeah, there you go. Okay, so it's going into this, which is to the east. So that means that we have V cross B is east because it says that it's a proton. Is that a positive or negative charge? Positive. So that means it's in that direction. So headed east. Are we then going to have to worry about that proton hitting us? Probably not, because there's a force to deflect it to the east. So how does the Earth's magnetic field shield us from the bombardment of cosmic rays? As long as we're close to the equator. But if we have that same particle and it comes here, that's almost but not exactly parallel to the magnetic field. Because it's not exactly parallel, there's going to be a force that's perpendicular to this and perpendicular to this. It's going to be a force that makes it move, and it's actually going to go around and spiral around the magnetic field line. And so it's going to keep following that magnetic field line and come in. So if you live here, it's going to pull it right in toward you. So if you're at the North or South Pole, you're going to not be shielded, but instead get the shower of the cosmic rays because of the Earth's magnetic field. But if you're in this region here, which is where the vast majority of the world's actually, if you want to be honest, The vast preponderance of the Earth's population lives between those lines. What, 80% of humans live between those two? And was it 10% in South America? The population and land masses are spread out that makes the northern hemisphere is much more common. So the last question, where on Earth's surface is the shielding least effective? Yeah, the poles, North and South Pole. Now a problem with actually doing some work. At a certain place, the Earth's magnetic field has a magnitude of 0.050 milliteslas, which would be 0.5 Gauss. That's why we have the Gauss. The field direction is 70 degrees below horizontal. Its horizontal component points due north. So if we make a picture, and I'm going to have here is north, here is down, here is up. Then it tells us the magnetic field is 70 degrees below horizontal. So there's the magnetic field in this region. And we have the magnetic field strength is 0.050 milliteslas. Find the magnetic force on an oxygen molecule. It's an ionized oxygen molecule. Why it's important that it's ionized? Yeah. If it had no charge, there'd be no force, right? It's negative charged. What's that mean? It's picked up an extra electron. It's negative. It's picked up an extra electron. It's not missing one. It's added one. And it has a velocity that's equal to 250 meters per second east. What direction is east going to be in my picture? Okay, so my velocity is like that.
No, sorry.
Yeah, you're right. It's out. I just trusted you.
Sorry.
Okay, so like that. And so we have find the magnetic force. We have two things to worry about. It's direction, it's magnitude. Let's do the direction first because we've been working on that the most. So what is the direction here? Caitlin. Okay, so you have your index finger pointing the direction of V, which is coming out. And then your middle finger, like this. So what direction is the thumb pointing? It's going to be 90 degrees. Right, we have my index finger is pointing out, right? And then my middle finger is pointing 70 degrees here. And so my thumb is up 90 degrees in the plane of my picture. And so it's going to be up here. So that's 20 degrees up from north. Just 20 and 70 is 90. So our direction is 20 degrees up from north. Except for one thing. What's the one thing I skipped? It's negative. Change the direction of the arrow, right? So now it's downward 20 degrees below south. So we have the direction. How about the magnitude? Jordan. What's the charge?
The charge is on. The electric field would be 150 newtons per coulomb. So that's the.
Well, that we're not looking at B yet. We're still looking at A. We have an oxygen ion. So what's its charge? It's a negative ion.
Negative 1.
Negative 1 electron. So minus 1.602, right? Times 10 to the minus 19. But I'm not going to put the minus sign in there because I'm just putting the magnitude to find the magnitude of the force. I already determined the direction. So I'm scratching out the minus sign. So I have V or Q, then V. What's my speed? Right here.
215 meters per second.
And then I have to multiply it by my magnetic field, 0.05 millitesla, which is 5 times 10 to the minus 6. 5? 5. Yeah. Was there a decimal there? Yeah, there was. So we have 2 sig figs. So now we just multiply that through. And of course, I don't know what the number is.
You also have to add a sign.
Yes, I do, but what's the angle between the two?
20 degree. No.
90 degrees. I didn't write it. We should have pointed that out. We have to look at the angle, but it's a 90-degree angle between horizontal and vertical. And in my picture, horizontal and vertical, I should say. In my picture, I have the velocity is this direction, and the magnetic field is perpendicular to that in the north down plane.
I get 0.893 8940.
Times 10 to the
That's all I get.
minus 19.
Okay. So
You got what?
2.0025.
No, I was looking at the wrong thing. She's right.
I'm getting 10 to negative 20.
Well, I would believe times 10 to the minus 20 because 50 times 250 is
I got 2.0025 times 10 to the negative 21.
7,500 is 7.5 times 10 to the minus 1. Multiply that by 1.6 times 10 to the minus. I don't know how we're getting so many different numbers. We should only have one. There can only be one, as they say in the movie. Can anybody decide what my answer should be?
It's minus 20.
I got minus 21.
I think it's minus 20. It's oh, my mistake. I put an extra 0 there. It's 0.0. And so, yes,
I don't getting that side.
that makes it minus 21. Yeah, so it's my writing.
Yes. Right.
Okay, so we have ourselves a force in newtons, and we have the direction. Now for part B, which Jordan wanted to answer, compare the magnitude of this magnetic force with its weight. 5.2 times 10 minus 25. I don't have to calculate it. Is that more or less than its weight?
No, it's more.
It's more. It's like 10,000 times more. Well, yeah. 4,000 times more. Something like that. So it's much, much more. So the weight is negligible compared to this force. And what about the electric force on it due to the Earth's fair weather electric field of 150 newtons per coulomb? What's the electric force on this? The magnitude. Force is what times what? Q times E for the electric force. And so that's going to be 1.602 times 10 to the minus 19. Once again, I'm just using the magnitude times 150.
Which is 2.40 times 10 to the negative 17.
That electric force is even much stronger. So the electric force is much stronger than the magnetic force, which is much stronger than the gravitational force. Which makes it clear why I said just ignore the gravitational force unless you're told to use it. What if you have, well, I'm just going to skip by this one. This one's useless to me. What if you have a particle that's moving perpendicular to the magnetic field? So I have a magnetic field that's pointing up and actually pointing down in this picture, and I have a particle that's moving horizontally. Using our right-hand rule, my V is going in the circle, so just going on the right-hand side of the circle here, my V is pointing up, my magnetic field is pointing into the page, so like this, and the force is to the center if it's a positive charge. So if it's a positive charge, the force to the center, when it moves up here, what direction is the velocity? It's tilted over, right? The magnetic field is still down, and my thumb still points to the center. If the force is perpendicular to the velocity, what does that do to the velocity? Couldn't hear you. That was Carrie, right? Or was Mom? Yeah, all it does is changes the direction of the velocity. The magnitude remains constant. So it's not going to do any work because it's not going to change its speed, but it's going to change its direction. So it's going to make the particle do a circle. And so since it's going to make it do a circle, we can take the magnitude of the force and the fact that if something's going in a circle, we know that the acceleration has to be the centripetal acceleration of v squared over r. And we can apply Newton's second law and say the sum of the forces toward the center is equal to mv squared over r. And the force toward the center, if it's perpendicular, sine theta is 90 degrees. So I'm going to have qvb equals mv squared over r. Therefore, the radius must be equal to mv squared over over qvb is equal to mv over qb. So it's going to go around a circle that depends on the mass, the speed, and the magnetic field, and the charge. Now, what if it was a negative charge instead of a positive charge? What would be different? Okay, it would point the opposite direction, so what path would it take? It'd be a clockwise circle instead of a counterclockwise circle. It'd still do the circle, but it would be the opposite direction. When I talked about a charged particle coming in, okay, keep going, coming in up here, the part of the velocity that is perpendicular to the magnetic field is what's making it do the circle. The rest of the velocity is what's making it keep going. And so it's the doing spirals around those magnetic field lines because of this process. How is this useful? Has anyone here ever used a mass spectrometer? This is one of the ways you can make a mass spectrometer. You put in particles, and if you know what the speed is, and you know what the magnetic field is, the radius is going to depend on the mass if they all have the same charge. We make assumptions that they have the same charge. If you've done much in mass spectrometry, you know that's not always true, so you have to be careful. So if you can get them all the same speed, you can find the mass from that. So it's very useful. So here's a mass spectrometer. You have a source of ions. You put them through an accelerating voltage to get them all going the speed you want. And in fact, I'll show you in just another slide how we can select to make sure they're the speed we want. And then you go into the magnetic field and you measure the radius. And that radius tells you what the mass is. This is a practical problem doing it. I'm not going to do the problem because I see I only have 6 minutes left. Here's a cyclotron. Back before Loma Linda built their proton accelerator, there was still bombarding tumors with charged particles. But instead of using protons, they used electrons. And so for those electrons, they speed them up by using this device here called a cyclotron. So how does the cyclotron work? You have what we call split Ds. You see each one of those chambers is shaped somewhat like a D. Okay, wrong color. Like a D and another D. So we call it split Ds. And you inject particles right in the, well, not exactly the center, but close to the center there. And you inject a particle, and between the two split Ds, you have an alternating voltage. So at one moment, you're going to have the D on the right is positive compared to the D on the left. A moment later, it's going to switch. So you put those particles in there, the positive particles, and they're going to be attracted to the negative side. Once they get in the negative side, because you have that external magnetic field, they're going in circles that depend on their speed. When it comes back around, it gets to that gap, and you have the frequency set so that it will change. So now it's on the positive side, the other side's negative, it gets accelerated across. Going from positive to negative, it picks up energy, so it goes faster. And so now it goes with a bigger radius, and each time it crosses that gap, it picks up energy because the voltage is switching back and forth in synchronization with the time it takes to do half of a circle. And so when it gets to the edge, when the radius gets really large, it's going really fast. And then they shoot those out and they aim them at the cancerous tumors in the people. So that's what a cyclotron is. Now, some people might be a little more familiar with Ghostbusters. In Ghostbusters, what they are supposed to have on their backs is one of these. They're accelerating electrons and shooting those electron beams at their poltergeists and whatnot. You guys have seen the movie, right? I haven't seen the recent one, by the way, but that's what a cyclotron is. It's a real device. It makes particles go really fast. I'm not sure why crossing the beams would be bad, but I think they said something about antiparticles, so maybe it was a special kind of cyclotron. So with this, you can make calculations on, okay, if you have this magnetic field and the maximum radius is that big, then going back to the equation that we had before, if you're using electrons and going back to this relationship here, you could solve it for the speed as a function of the electron's mass, charge, and your external magnetic field and the radius. So that's what this question is asking you to do. It's not asking you to calculate the cyclotron frequency. That will come up later, not this chapter. Okay, final thing for today. If I have a charged particle moving in both an electric field and a magnetic field, I will have a force through the electric field and a force through the magnetic field, just like we saw when we did the problem previously. And so if you have it moving with the magnetic field and the electric fields perpendicular to each other, then you will have the force of the electric field and the force of the magnetic field also, well, not perpendicular now, but opposite each other. And that allows us to do something cool. We can reach an equilibrium where a certain speed will have a net force of 0, and thus just keep going a straight line. If it's going too slow, what does that do to the magnetic force? What happens to magnetic force if the speed slows down? It decreases. So now the electric field is going to have a stronger force, and it's going to go the direction of the electric field. If it's going too fast, then the magnetic force is stronger than the electric force, and it will go away from the electric field. But if it's at just the right speed, it'll balance. And so we say the total force is the electric force plus the magnetic force. And then we just put in the two equations. Electric force is QE, and the magnetic force is QB. And this is set equal to 0 because of equilibrium being the situation we want. And so that sets a relationship between the electric field strength, the velocity in the magnetic field, for it to have a constant velocity to be in equilibrium. And I have to stop here. I'll see you on Monday. Have a happy Sabbath.